Welcome back to Chapter 3 of Principles of Mathematical Analysis. In the previous section, we set up the general theory of infinite series, partial sums, the Cauchy criterion, the divergence test, and the comparison test. The comparison test told us that to decide whether a series converges, it helps to compare it to a series whose behavior we already understand. In this section, we stock our toolbox with the most important reference series for non-negative term comparisons. We will prove 4 results: the geometric series, the Cauchy condensation test, the p-series test, and a refinement involving logarithms. Together, these cover almost every non-negative term series you will meet in practice. Here is the plan. We open with motivation, why non-negative term series are special, and what we hope to gain from the section. The first stop is the geometric series, Theorem 3.6, our most basic reference series. We then turn to Theorem 3.27, the Cauchy condensation test, which lets us decide convergence by looking at a thin subsequence of the original series. We apply the condensation test twice, first to get Theorem 3.28, the p-series test, and then to get Theorem 3.29, the logarithmic series test. We close with a brief discussion of the so-called boundary between convergent and divergent series and a summary of what we have built. Recall the comparison test from the previous section. To prove that a series converges or diverges, we compare it term by term to a series whose behavior is already known. The whole strategy is only useful if we have a stockpile of reference series whose behavior we have nailed down. Building that stockpile is what this section is about. Non-negative terms have one big technical advantage. If every term is at least 0, then each new partial sum is at least as large as the previous one, so the sequence of partial sums is monotonically increasing. Monotone sequences are much easier to handle than general sequences. They converge if and only if they are bounded above. This is exactly Theorem 3.24 from the previous section. A series of non-negative terms converges if and only if its partial sums form a bounded sequence. This single fact removes all the epsilon machinery and turns convergence questions into bounded questions. It is the workhorse behind every proof in this section. Our goal in this section is to nail down 4 families of reference series: the geometric series, the condensation principle, the p-series, and the logarithmic series. The first is concrete and classical. The second is a powerful general tool. The third and fourth are applications of the second. With these in hand, almost any non-negative term series you meet in practice can be decided by comparison. Let us begin with the simplest example. The geometric series is the most basic infinite series in all of analysis. The terms are powers of a fixed number, x. We want to know 2 things: for which values of ex does the series converge, and when it does, what is the sum? The reason the geometric series is tractable is that its partial sums have a clean closed form. 1 plus x plus x squared all the way to ax to the en can be written as a single fraction with no summation symbol. From there, the limit is straightforward. Here's the statement. For x between 0 and 1, not including 1, the geometric series converges and its sum is 1 over 1 minus x. For x greater than or equal to 1, the series diverges. Notice the asymmetry of the conclusion. When it converges, we do not just know it converges, we have an exact formula for the limit. That makes the geometric series an especially useful reference for comparison arguments. The plan is short and concrete. First, we compute a closed form for the partial sum S sub n when x is not equal to 1, using a standard algebraic trick. Second, we let n go to infinity in that closed form, which immediately tells us whether and to what the series converges. Third, the case x equals 1 has to be handled separately because the closed form fraction has a 0 in the denominator there. But in that case, the series is just 1 plus 1 plus 1 forever, which obviously diverges. Step 1 gives us a closed form for the partial sum. The trick is the telescoping identity highlighted on the slide. Multiply the partial sum by 1 minus x and distribute. You get the sum 1 plus x squared up to x to the n, minus the same sum, shifted up by 1 power. Every middle power of x appears once with a plus sign and once with a minus sign, so it cancels. What survives is just the 1 from the bottom of the first sum and the minus x to the n plus 1 from the top of the second. Dividing by 1 minus x, which is non-zero since we assumed x is not 1, gives the formula on the slide. The entire partial sum is now captured by a single fraction, and that is the only real computation in the whole proof. Step 2 is where the limit actually happens. We let n grow without bound in the closed form from step 1. And notice that the whole expression is controlled by a single moving part, the power x to the upper en plus 1 sitting in the numerator. When x lies between 0 and 1, repeatedly multiplying by a number smaller than 1 drives that power to 0. This is one of the special limits we established earlier in the chapter, so the numerator settles down to 1 and the fraction approaches 1 over 1 minus x, which is exactly the sum claimed in the theorem, when x is greater than 1. The same power instead grows without bound, so the partial sums run off to infinity, and the series diverges. The only value still untreated is the boundary case, x equals 1, and we turn to it next. Step 3 is the boundary case, x equals 1, which the closed form formula does not handle because the denominator vanishes there. But we do not need any machinery. Each term is just 1. The partial sums are 1, 2, 3, 4, and so on, and they go to infinity. The series obviously diverges. Combining the three cases, we have proved the theorem. The geometric series converges precisely when x is strictly less than 1, with sum 1 over 1 minus x. Here is the geometric series with x equal to 1/2 pictured on the number line. The blue dots are successive partial sums. The first is 1, then 1 1/2, then 1 3/4, then 1 7/8, and so on. The red dot at 2 is the limit, since 1 over 1 minus 1/2 equals 2. The orange brackets below the axis show how each new term covers exactly half of the remaining gap to 2. This picture makes Zeno's paradox feel almost obvious in hindsight. You never finish the walk in any finite step, but you do approach the destination as a limit. Two quick numerical examples. With x equal to 1/2, the sum is 1 over 1 minus 1/2, which is 2. With x equal to 1/3, the sum is 1 over 1 minus 1/3, which is 3/2. Both fall out of the formula instantly. The geometric series will appear constantly throughout the rest of the chapter, especially when we prove the root test and the ratio test. Whenever we want to show a series converges fast, the standard move is to compare it term by term to a geometric series with ratio strictly less than 1. Most non-negative term series you meet in practice have the extra property that the terms are decreasing. The second term is no bigger than the first, the third is no bigger than the second, and so on all the way down to zero. In that monotone setting, we can do something surprising. We can decide convergence by looking only at a thin subsequence of the original terms, sampled at powers of 2. That is the content of Cauchy's condensation test, which we state next. Here is the theorem. We assume the terms a sub n are non-negative and weakly decreasing. The claim is that the original series and the condensed series, which uses only the first, second, fourth, eighth, 16th, and so on terms, each multiplied by the matching power of 2, both converge or both diverge. The striking feature is just how thin the condensed sample is. Even though the condensed series only inspects terms at the powers of 2, it captures the full convergence behavior of the original series. The proof is short and uses nothing more than careful grouping. Here is the picture behind the proof. 2 slightly different groupings do all the work. For the upper bound, shown on the top line, we group the terms into blocks that start at a power of 2. A single term, a sub 1, then the block of length 2 starting at a sub 2, then the block of length 4 starting at a sub 4, and so on. Because the sequence is decreasing, every term in such a block is at most its first term. So each block of length 2 to the k is bounded above by 2 to the k copies of a sub 2 to the k. Reading off the bounds gives the condensed series exactly. For the lower bound on the second line, we shift the grouping by 1 step, so each block ends at a power of 2 instead of starting at 1. Now every term is at least the last term, and the block sums are bounded below by 2 times a sub 4, then 4 times a sub 8, then 8 times a sub 16, and so on. Reading off these bounds gives the same condensed series, now shifted by 1 place. Both groupings, upper and lower, reproduce the condensed series up to a factor of 2. That 2-sided sandwich is the whole proof. To prove the theorem we use Theorem 3.24, which says a non-negative term series converges if and only if its partial sums are bounded. So we just need to show that the partial sums of the original series are bounded if and only if the partial sums of the condensed series are bounded. Let Sn sub n denote the partial sum of the original series, and T sub k denote the k, the partial sum of the condensed series. The whole game is to bound S sub n by T sub k, and vice versa. Step 1. Pick any n and choose k large enough that 2 raised to the k plus 1 power exceeds n. Group the first n terms into blocks of lengths 1, 2, 4, up to 2 to the k. Inside each block of length 2 to the j. Every term is at most a sub 2 to the j, since the sequence is decreasing. So the block sum is at most 2 to the j times a sub 2 to the j. Adding up all the block bounds gives exactly T sub k. This is the first half of the sandwich. S sub n is at most T sub k. Step 2 is the matching lower bound. Now choose n larger than 2 to the k. Group the first n terms into blocks of lengths 1, 1, 2, 4, all the way up to 2 to the k minus 1. This time, the smallest term in each block is its last term, so the block sum is at least its length times that last term. After this step, we have a raw lower bound of a sub 1 plus a sub 2 plus 2 times a sub 4 plus 4 times a sub 8, and so on. To match the form of T sub k, we deliberately weaken a sub 1 down to half of itself. That costs nothing since a sub 1 is non-negative, and the surviving combination is precisely 1/2 of t sub k. Rearranging twice the n, the partial sum of the original series is at least t sub k. That is the other half of the sandwich. Combine the two inequalities. Either both sequences s sub n and t sub k are bounded, or both are unbounded. There is no third option, because each one bounds the other within a fixed multiplicative constant. By theorem 324, boundedness is the same as convergence for these monotone partial sums. So the original series and the condensed series converge or diverge together. That completes the proof. The p-series test pins down exactly when the prototype series 1 over n to the p converges. The answer is, it converges if p is strictly bigger than 1, and diverges if p is at most 1. Two cases are especially memorable. When p equals 1, we get the harmonic series, 1 plus 1/2 plus 1/3, and so on, and the theorem says it diverges, even though the terms go to 0. When p equals 2, we get the Basel series, which Euler famously summed to pi squared over 6, though we will not need the exact value here. Step 1 disposes of the trivial range p less than or equal to 0. In that case, the exponent is at most 0, so 1 over n to the p is at least 1 for every n. The terms do not even go to 0. So by theorem 3.23, the divergence test, the series diverges. From here on, the interesting question is what happens for p positive. Step 2. For p positive, the terms 1 over n to the p are positive and decreasing, so Cauchy's condensation test applies. Plug a sub 2 to the k equals 1 over 2 to the kdp into the condensed sum on the slide. The factor of 2 to the k out front combines with the 1 over 2 to the kp inside to give 2 to the power 1 minus p times k. So the condensed series is just a geometric series with ratio s equal to 2 to the power 1 minus p. Step 3 finishes the proof using the geometric series test from earlier in this section. The condensed series is geometric with ratio 2 to the power 1 minus p, and a geometric series converges exactly when its ratio is strictly less than 1. Now, a power of 2 is less than 1 precisely when its exponent is negative, so the condition becomes 1 minus p less than 0, which rearranges to p greater than 1. Combining this with step 1, where we ruled out the non-positive exponents, the p series converges if and only if p is greater than 1. It is worth pausing on what just happened. An entire family of convergence questions collapsed through condensation onto the single fact we already knew about the geometric series. Here is the landscape of the p series at a glance. The horizontal axis is the exponent p. On the left, in red, is the region where the series diverges, namely p at most 1. On the right, in green, is the region where the series converges, namely p strictly greater than 1. The orange dashed line at p equals 1 is the critical boundary, and crucially, the boundary itself belongs to the divergent side. The harmonic series, sitting right at p equals 1, just barely fails to converge. The Basel series at p equals 2 is safely inside the convergent region. Before stating the next theorem, a small note about notation. In this book, the symbol log always means the natural logarithm, that is, logarithm to the base, e. This is consistent with most analysis texts. The number e itself is defined in the next section, but its existence is not needed for what follows. We only use that the logarithm is a monotonically increasing function. Notice also that the series has to start at n equal to 2, because at n equal to 1 the logarithm is 0, and we would be dividing by 0. Theorem 329 is a more refined cousin of the p-series test. The terms are 1 over n times log of n to the p power, which is smaller than 1 over n to the p, but only barely. The extra logarithm factor decays very slowly. Remarkably, the threshold is exactly the same as in Theorem 328. The series converges if and only if p is strictly greater than 1. The proof is one line of algebra. The logarithm is increasing, so its reciprocal is decreasing, and the whole sequence 1 over n log n decreases, so Cauchy condensation applies. Plug in a sub 2 to the k equals 1 over 2 to the k times log of 2 to the k to the p power. The factor 2 to the k outside cancels the 2 to the k inside. The log of 2 to the k simplifies to k times log 2, and we are left with a constant times the sum of 1 over k to the p. By the p-series test that converges if and only if p is greater than 1, and the theorem follows. The condensation trick is not a one-shot device. It can be applied again and again. Start from the borderline divergent series, 1 over n times log n, and slip one more slowly growing factor, the log of log n, into the denominator. That gives the series on the slide, equation 12. You might hope that this extra factor finally tames the divergence, since it makes the terms even smaller. It does not. Running the condensation argument one more time reduces equation 12 to a harmonic-type series, which we already know diverges. So equation 12 diverges as well, even though its terms shrink faster than those of any divergent p-series. But if we square the iterated logarithm, we tip over into convergence. The series in equation 13 converges, again by the same condensation argument, reducing to a p-series with exponent 2. So the procedure tells us, by iteration, exactly where the borderline is at each level of nested logarithms. Look closely at the two examples we just saw. Their terms differ only by an extra factor of log n, yet one diverges and the other converges. The gap between divergence and convergence is incredibly thin. Worse, we can iterate the trick. Sticking in more nested logarithms produces matched pairs of divergent and convergent series whose terms differ by less and less. The natural question is there some ultimate borderline series, a convergent series whose terms are larger than every divergent series in this family? The answer is no. No matter how we try to make the notion of a boundary precise, no such boundary exists. There is no slowest convergent series and no fastest divergent series, even among monotone series. Exercises 11 Part B and 12 Part B in this chapter sketch one way to make that statement precise. For a deeper discussion, Rudin points readers to Knopp's classic book on infinite series, particularly Chapter 9, Section 41. Let us review what we have collected. First, the geometric series, our most basic reference. It converges for x in the interval from 0 to 1, not including 1, and diverges otherwise. When it converges, we know its sum explicitly, 1 over 1 minus ex. This is the only one of our reference series for which we have a closed form sum. Second, the Cauchy condensation test. For non-negative decreasing terms, the original series and the condensed series, sampled at powers of 2, converge together. This is the engine that drives the rest of the section. It converts questions about slow decaying series into questions about geometric or p-type series. Third, the p-series test. The series 1 over n to the p converges precisely when p is strictly greater than 1. The harmonic series at p equals 1 just barely fails to converge, and this fact will haunt us many times in the rest of the book. Fourth, the logarithmic series. Inserting a log n to the p factor in the denominator shifts the threshold downward only slightly. The cutoff is still p equals 1. We also saw that the procedure iterates indefinitely, with no ultimate boundary between convergent and divergent series. Coming up next, the number e gets its definition, and we estimate just how badly it fails to be a rational number. That sets the stage for the root and ratio tests later in the chapter.